Hey guys, it's Catherine. I'm going to be explaining the area of Koch'sSnowflake today and going in depth with how that works. And Blaine will be explaining the perimeter of Koch'sSnowflake. So sit back, relax, and enjoy the math.
The first step in creating one side of Koch'sSnowflake is to begin with an arbitrary line. Once we have that line, we can select its endpoints and use the dilation tool to dilate the line by 1/3 and then by 2/3. Doing this gives us 2 points along the segment, both 1/3 of the original length from each endpoint. By selecting the left point on the line as your center for rotation, we can rotate the right point around 60 degrees to mark the third vertex of what will become an equilateral triangle. By connecting the lines with a new dot, we can form that triangle. To complete the first iteration, we need to hide the base of the equilateral triangle. Once that is done, we can use the custom tool in Sketchpad to replicate this for each of the new line segments, creating 4 new triangles to go with the one we just made. Hiding these bases will give us the second iteration of Koch'sSnowflake. Using the tool one last time along each of the segments gives us the third and final iteration. It will create 16 new triangles on top of the 5 we already have for 21 total triangles. Removing the bases will complete our construction and give us one side of Koch'sSnowflake with 3 iterations. Using 60-degree rotations around the endpoints of the original line segment, we can create a completed Koch'sSnowflake with 3 iterations.
Now we will explore the area of Koch'sSnowflake. Now that we know how to create Koch'sSnowflake, we'll look at the area. So we'll start with the area of a side length of 1 on the triangle. So the area will be the square root of 3/4 because it's 1/2 base times height. Now this is a triangle with the iteration of 0. So now when we move on to an iteration of 1, we will add the new triangles, and there will be 3 of them, to the original. Each of the new triangles has a third of the side length of the original. So that is why it's 1/3 squared times the square root of 3/4 times 3, which is the number of triangles. Now when we move on to the second iteration, it will be a very similar pattern, except it will not be 1/3, it will be 1/9, because we'll be taking a third of the 1/3. And there will also now be 12 new triangles instead of 3. So it's 3 times 4. Now we'll find that this pattern is repeating itself as we move on to the next iteration. So the third iteration, just like the others before, adds the previous area plus the new area that's being derived. And we're finding this by taking the third of the side length that was before, squaring it, and multiplying it by the original area, and then the number of triangles that are now in the snowflake. So we can find that the area is given by the formula on the screen right now, and that it's 1/3 to the n squared times square root of 3/4 times 3 times 4 to the n minus 1, all added to the area of the triangle preceding it. So now we're going to work towards the limit. We're going to start with the equation that I just used before, and we'll start simplifying it. So first we will move the squared down and evaluate it. So it's 1/3 to the 2 times n. So now we'll just move the equation around for a little bit of easier working so that the square root of 3/4 is in front. The 3 is now on the denominator as 3 to the 2n minus 1 because we subtracted the 3 from the numerator. So 4 to the n minus 1 can be also written as 2 to the 2n minus 1 using exponent properties. So we'll put that in to the original as 2 to the 2n minus 2. So now that the exponents on the 2 and the 3 are very similar, we're moving right along. So 2 to the 2n minus 2 can also be written as 2 to the 2n times 2 to the negative 2. So when we simplify that a little bit and get it to the right exponent we want, it will be to the 2n minus 1 times 1 half. So we'll plug this back in to our original equation. So we have the square root of 3 over 4 times the 2/3 to the 2n minus 1 times 1 half. So this simplified will be our limit equation. So now that we have the equation for the limit derived, we'll plug that into the equation for n when it goes to infinity. So we have the square root of 3 over 4, which is our original area, plus the sum of the square root of 3 over 8 times 2 over 3 to the 2n minus 1 as n goes to infinity and n is 1. So we find that the area of the snowflake is 2 times the square root of 3 over 5. So the area is finite.
Now for the fun part, deriving the perimeter. To derive a general formula for the perimeter of Koch'sSnowflake, we need to start at n equals 0. At n equals 0, the side length is 1, and since there's 3 sides, Koch'sSnowflake at n equals 0 is 3. 3 times 1 since it's an equilateral triangle. When we perform the first iteration, the line segments all have a length of 1/3 the original length. So there are 4 sides at 1/3, so there's 4/3 total length. Multiplied by 3 again for the 3 sides, and we get a total perimeter of 4/3 times 3, which is just 4. Performing another iteration for n equals 2, we get side lengths of 1/9 of the original length. And this gives us 16 sides, so the total length is 16 lines, multiplied by 3 for the perimeter, and we get 16/3. Performing one last iteration, the side lengths are now 1/27 of the original length. And there are 64 sides now with all the triangles, so the total length is 64/27. Multiply it by 3 for the perimeter at n equals 3, and we get a perimeter of 64/9. Now if you look at the side lengths for each iteration, it is 4/3 the original side length raised to some exponent, and that exponent always is n. So we can assume that the general formula for perimeter of Koch'sSnowflake is 3 times 4/3 s to the nth power, where s is the original. Taking the limit of 3 times 4/3 to the nth power as n goes to infinity, we find that the perimeter also goes to infinity. Therefore, Koch'sSnowflake is a figure with finite area but infinite perimeter.